Deep within the concrete sarcophagus of Chernobyl, a hidden chamber emits a signal that's alarming scientists worldwide. No human, not even a robot, can enter this forbidden space, yet sensors outside detect a slow, relentless rise in neutron radiation, an ominous sign that a nuclear fire, thought contained, might be rekindling. Scientists compare it to the smoldering embers of a nuclear inferno that has burned for 40 years. Most troubling is not just that it burns, but that the €1.5 billion protective dome, designed to contain it for a century, is no longer fully effective. On April 26, 1986, the fourth reactor of the Chernobyl nuclear power plant exploded. This fact is widely known by anyone familiar with the name Chernobyl. However, few consider what became of the material left inside. The explosion ripped off the reactor lid, weighing 2,000 tons, tossing it into the air like a cork from a bottle. A radioactive cloud blanketed half of Europe. Scientists estimate that 400 times more radioactive material was released into the atmosphere than from the combined atomic bombings of Hiroshima and Nagasaki. Yet, even after such a massive release, 95% of the nuclear fuel remained inside the building. 170 tons of irradiated uranium were still there. To visualize this weight, imagine 40 fully loaded dump trucks lined up, but instead of gravel, each carries material capable of killing all living things for kilometers around. And that material is still present today. In the initial hours after the explosion, the molten fuel, control rods, zirconium, graphite, and sand used in an attempt to extinguish the fire, mixed into incandescent lava. It burned through floor after floor, flowing ever deeper into the reactor building. The temperature of this mass exceeded 1,200 degrees Celsius, melting steel structures and penetrating concrete slabs 2 meters thick. The lava flowed through corridors, seeped into cable channels, and permeated ventilation shafts. It behaved like a living entity, searching for a path downward. When the mass finally cooled, it transformed into a substance that exists in only 5 places on Earth. Scientists named this substance corium, derived from the word core. It forms only when a nuclear reactor's core melts down. In all of human history, this has occurred precisely 5 times, once at Chernobyl, once at 3 Mile Island in Pennsylvania, and 3 times at Fukushima. Corium cannot be replicated in a laboratory in its true form. One scientist involved in creating a lab-scale replica compared the difference between the original and the model to that between real sports and a video game. 8 months after the accident, a team of researchers descended into a corridor beneath the reactor. 2 dosimetrists, Mikhail Kostyakov and Vladimir Kabanov, carried a device designed for a maximum of 3,000 Roentgens per hour. They were 12 meters below the core and 15 meters horizontally from it. Even at that distance, their dosimeters showed 25 Roentgens per hour. They found a staircase leading up to room 217 halves and began to slowly ascend, holding the device in front of them. With each step, the readings on the dosimeter climbed faster and faster, until the device maxed out and broke down. They abandoned it on the steps and fled. Imagine what a person feels when equipment designed for extreme conditions breaks because of what awaits above. They didn't know they had just discovered the elephant's foot. It was later revealed that a 2-ton mass awaited them around the bend of the staircase. It was black, lumpy, covered in something resembling both tree bark and glass. It was named the elephant's foot for its shape, reminiscent of a giant animal's foot. At the moment of its discovery, it emitted about 10,000 Roentgens per hour. For comparison, a single chest X-ray gives you 0.01 Roentgens. 10,000 Roentgens per hour means a million such X-rays every 60 minutes. 5 minutes near this mass guaranteed death, not in years, but in a few agonizing weeks. But the elephant's foot was merely a fragment. Corium spread throughout the building like volcanic lava, solidifying in dozens of rooms on different floors. It formed stalactites hanging from ceilings, horizontal flows that breached walls, and vertical columns that pierced through several levels. The main mass accumulated in a room directly beneath the core, in room 305/2. Scientists estimate that approximately half of all the nuclear fuel is located there. And it is precisely from this location that the alarming signals are now emanating. If you're intrigued by inaccessible places and the secrets they hold, consider subscribing to Cosmic Riddles so you don't miss our next video. In 1996, 10 years after the disaster, radiation specialist Arthur Corneve descended to the elephant's foot with a camera. The photograph he took traveled the world. In the image, the silhouette of a person next to the lumpy, dark mass is barely discernible. The image is blurry and grainy, not due to a poor camera. The graininess is created by the radiation itself, ionizing the air and bombarding the camera's sensor. The camera was literally photographing invisible death. Corneve survived, though he developed cataracts and a host of severe radiation-induced illnesses. When asked how he worked near such high levels of radiation, he replied, "Sometimes we used a shovel, and sometimes we just kicked pieces of radioactive debris with our feet." When the first samples of corium were brought to the laboratory, something unexpected was discovered. The mass was so hard that scientists had to shoot it with an automatic rifle to break off a piece for analysis. No scientific experiment in history had ever begun in such a manner. But over the past decades, the corium has changed. Under the influence of its own radiation, humidity, and time, it has begun to degrade. From a hard ceramic that bullets couldn't penetrate, it is gradually transforming into a fine powder. And this powder remains lethally radioactive. If it were to become airborne, collecting it would be virtually impossible. Today, the elephant's foot itself emits between 300 and 800 roentgens per hour, depending on the measurement point. This is dozens of times less than in 1986, but still lethal with prolonged contact. Its surface has cracked and is covered with yellow spots of new minerals. Inside the mass, zircon crystals and uranium oxide dendrites have begun to grow, forming, breaking down, and reforming. Corium is not inert, it continues to change, and scientists still cannot precisely predict what it will become in 50 or 100 years. In 1986, a concrete sarcophagus was built around the destroyed reactor in 206 days, using 400,000 cubic meters of concrete and 7,300 tons of metal structures. Construction took place under unimaginable conditions. Due to the horrific levels of radiation, workers could not remain on site for more than a few minutes. They were called liquidators, and hundreds of thousands of people participated in the construction. Each person ran onto the site, performed a single action, and returned. The next person took their place and did exactly the same. Some received their permissible annual radiation dose in just 40 seconds of working on the reactor roof. Bolts were not tightened by hand, seams were not welded. Everything was done remotely using cranes and mechanisms, without precise fitting. The sarcophagus was not hermetically sealed from day one. Rainwater seeped through cracks in the roof, washed over the radioactive masses, became contaminated, and then drained through cracks in the floor into the soil. You might wonder why it was built at all if it couldn't fully isolate the reactor. It was constructed as a temporary solution, designed for 30 years. However, this temporary solution lasted longer than 3 decades, and by the end of the 1990s, it began to collapse. The roof sagged. A supporting beam, which the builders nicknamed the Mammoth, rested on the reactor's western wall, already damaged by the explosion. The structure, intended to protect the world from radiation, itself became a threat of collapse. It was then that the international community decided to build a new dome. In 2016, the new safe confinement, NSC, was installed over the old sarcophagus. This arch, 105 meters high and 257 meters wide, is one of the largest movable structures ever built by humans. It was assembled away from the reactor on special rails and then slid over the sarcophagus so that construction workers were not exposed to radiation. More than 40 countries invested €1.55 billion in this project. The total cost of the entire liquidation plan, including infrastructure, amounted to €2.7 billion. Inside the dome, 2 enormous bridge cranes were installed for remote dismantling. The structure was designed to last 100 years. During this time, engineers planned to dismantle the old sarcophagus from within using remote cranes and hydraulic shears. Operators were to manage the process from a shielded room, without approaching the debris. The deadline for dismantling was set for October 2022. For the first time in decades, humanity seemed to have a plan, a truly thoughtful one, backed by the money and technology of 40 countries. The dome stood, the sensors worked, the cranes awaited their hour. Chernobyl was finally under control. But then engineers encountered a problem no one had foreseen. When the new dome blocked access to rainwater, the moisture level inside began to drop. It would seem that a dry reactor is safer than a wet one, but the physics of nuclear reactions does not work as common sense suggests. To understand what is happening, one needs to know a particular characteristic of neutrons. A neutron ejected from a uranium nucleus after fission travels at immense speed. At such speeds, it typically flies past other nuclei without hitting them. But if a neutron passes through water, the water molecules slow it down, much like a dense medium slows a bullet. A slow neutron is much more likely to hit a uranium nucleus and split it. This fission will release 2 or 3 more neutrons, and the process repeats. This is a chain reaction. When there is too much water, it not only slows neutrons but also absorbs them, and the reaction dies down. When there is no water at all, neutrons fly too fast and skip past the nuclei. But between these extremes, there is a dangerous intermediate range where conditions become ideal for a self-sustaining chain reaction. In nuclear physics, this is called criticality, and it is one of the most dangerous states of matter. The specter of criticality has haunted Chernobyl from the very beginning. In June 1990, after heavy rainfall, sensors recorded a sharp spike in neutrons in one of the rooms containing corium. A scientist rushed inside and manually sprayed a solution of gadolinium nitrate directly onto the radioactive mass. Gadolinium absorbed the neutrons, and the threat receded. After this incident, gadolinium nitrate sprayers were permanently installed on the sarcophagus roof, but the solution cannot penetrate rooms filled with concrete debris. When the new dome blocked access to rain in 2016, specialists expected that without water, neutron activity would decrease. But exactly the opposite of what was expected occurred. As the corium dried out, it began to approach that dangerous intermediate point. The exact mechanism is not yet fully understood, but the data is unequivocal. Since 2016, sensors have recorded a steady increase in neutron radiation in room 305/2. In 4 years, the readings have almost doubled. Scientists from the Institute for Safety Problems of Nuclear Power Plants describe the situation without euphemisms: we cannot rule out the possibility of an accident. A repeat of 1986 will not happen, scientists are confident of this. But if the reaction accelerates uncontrollably, the heat from the nuclear chain reaction will evaporate any remaining water within the corium. This would, by itself, stop the process. However, the explosive wave could collapse unstable parts of the old sarcophagus, which still stands inside the new dome, and the collapse would stir up tons of radioactive dust that have accumulated there for 40 years. And if the hole in the dome is not sealed by then, this dust would escape outside. The increase is slow, and specialists have time to find a solution. But the problem is that this room is completely inaccessible. The radiation inside is too high even for robots, and the fuel is buried under several meters of concrete debris. Previously, when neutron levels sharply rose after heavy rains, specialists were sent into dangerous zones. Among colleagues, he was unofficially called the stalker, because he went where no one else would. He would rush into the irradiated corridor and spray the gadolinium nitrate solution, which absorbs neutrons, then run back, receiving in a few minutes a dose that an ordinary person would not accumulate in a lifetime. But there is no access to room 305 halves even for such a desperate operation. The corium there is buried under rubble, and spraying anything onto its surface is impossible. One idea involves creating a robot capable of withstanding extreme radiation and drilling a hole into the corium. Boron rods, which absorb neutrons and act as a brake for the chain reaction, are planned to be inserted into these holes. It sounds like a task from a science fiction movie, but it is the real plan of real engineers. And while they searched for a solution, something unexpected occurred. On February 14, 2025, at 1:30 in the morning, observers from the International Atomic Energy Agency heard an explosion over the fourth reactor. An unmanned aerial vehicle struck directly into the protective dome. The impact pierced both the outer and inner layers of the structure, leaving a hole approximately 6 meters in diameter. The roof insulation caught fire and smoldered for 2 weeks after the impact. The insulation proved to be flammable, and the fire spread within the roof layers, where it was difficult to detect without special equipment. Thermal imagers were used for extinguishing, directing water precisely at the hotspots because approaching closer was too dangerous. Environmental radiation levels, according to the agency, remained within normal limits, but this does not mean that everything is fine. In December 2025, the International Atomic Energy Agency published an official conclusion: the structure, designed for 100 years, had lost its primary safety functions, including its ability to contain radioactive materials. It had stood not for 100 years, but for less than 9. The structure was designed for earthquakes, hurricanes, and a century of adverse weather. But it was not designed for human memory to be shorter than the half-life of cesium. The load-bearing frame was not damaged. Monitoring systems continue to operate. But a 6-meter hole means that rainwater is once again entering, which means the humidity level in the Corium rooms is again beginning to change unpredictably. How this will affect the neutron reactions, which were already increasing, scientists do not yet know. The European Bank for Reconstruction and Development has promised to allocate funds for the dome's repair in 2026, but repairing a protective structure over a nuclear reactor in an active conflict zone creates an entirely different level of complexity. The exclusion zone has been closed to visitors since 2022. The power supply to the facility has been repeatedly interrupted due to shelling of a neighboring city. Without electricity, cooling and monitoring systems cease to function. At such times, personnel switch to emergency diesel generators. The head of the International Atomic Energy Agency has called these generators the last line of defense for nuclear safety. And this last line of defense is being activated with alarming regularity. The situation at Chernobyl today resembles a problem where all solutions are simultaneously correct and impossible. To remove the fuel, one must get inside. To get inside, one must reduce the radiation. To reduce the radiation, one must remove the fuel. And while this vicious circle remains unresolved, the corium continues to degrade and turn into dust. Scientists plan to complete the full liquidation of the consequences by 2065, but with each passing year, that date looks increasingly conditional. Beneath the damaged dome lies a substance that did not exist before 1986 and which no one can remove. Within this mass, nuclear reactions smolder, having not ceased for a single day in 40 years. The protection, meant to close the problem for a full century, has been breached. And engineers still haven't figured out how to extract the fuel from a room that cannot be entered. Chernobyl is commonly considered a disaster of the past, a textbook event, a photograph that seems to recede further with each decade. But the reactor has not read textbooks. It knows nothing of jubilees or anniversaries. It lives by the laws of physics, which are indifferent to the promises of engineers and the plans of politicians. And while we discuss deadlines and budgets, 170 tons of nuclear fuel continue to smolder in the darkness. Patiently, indifferently, on its own schedule. And that schedule is measured not in years or decades, but in millennia.